Hi, John Capobianco here, and there's a few new models, some new announcements that have come out recently that I'm going to explore and build into my consensus algorithm. Now, we're going to look at Phi4. So Phi3 was from Microsoft, the first small language model. Phi4 is another small language model, comparatively speaking, to other models. And apparently it's incredible and it has some great ratings. So we're going to see if Phi4 can interpret PCAPs, network packet captures. The other model I'm going to explore is one out of China called DeepSeekV3. Now, this is making all kinds of news and ruffling feathers at an international scale because it appears that China is doing this for a lot less cost on a lot less performant equipment, but they've been able to make a model that they've released and open sourced. So we're going to look at the models, we're going to look at some articles and some news, and then we're going to incorporate these two new models into the packet Kates system and compare them to some other models. All right, let's take a look. So Phi4 was just released. The article came out December 12th in 2024, and I would recommend reading this article, and we can see where Phi4 offers quality results at a small size. So compared to a 70 billion or a 72 billion instruct set, we can see how well this small Phi4 model performs, right? And here's the average performance indications. And it talks about safely and responsibly. And I always loved Phi3 because of the way they trained the model. It's not just garbage from the internet. Microsoft uses text and uses a lot of other sources other than the raw internet. So it's been on Hugging Face. We can check the model here on Hugging Face. It's a 14 billion parameter model. Now this is up significantly from Phi3, but comparatively it's still rather small. 16,000 context for tokens. And it's actually been added to Ollama just yesterday. So the other model we're going to look at is DeepSeekV3. 60 tokens per second, enhanced capabilities. There's all kinds of information you can see here. And it is available on Hugging Face as well. And we can see that it's, well, that's a big one. There's a smaller model available on Ollama. So let's go to Ollama, and what we're going to do is search for models, and we're just going to look for Phi4, right? 14 billion parameters, state-of-the-art model from Microsoft that is open source. So we're going to be able to pull this model from, and then let's look for DeepSeekV3. Let's just look for DeepSeek. There should be a V3 on here that we can use. And how big is this one? Okay, 3.2 billion parameters. I'm not sure if this is the official DeepSeek V3 that we should use. There's different DeepSeek V coders. So I do need to make note of what we need to run here in our command. And we're going to switch over to our code and add these two models to our jukebox using Kubernetes. So I'm going to switch into my packet Kate, and this is going to be coding for the next few minutes. Just copy and paste. I'm not going to really be doing a lot of coding, but there are some files I need to modify. So the first thing I'm going to do is modify the Nginx reverse proxy. And I'm just going to copy this 2 times. And we're going to call one of these the Phi4 server, and the other one the DeepSeek server. We then need to go down here and do the same thing for the actual configurations of these. So I need to go here and give it 2 new locations in the reverse proxy. And we want to match those. So this is going to be Phi4, Phi4, Phi4. And then these next three Mistral references we're going to change to DeepSeek, DeepSeek, and DeepSeek. And then we need the back end. So we're going to do the same thing here and make two new back ends for the API communication with the front end. So this will be the last of the edits here, Phi4, Phi4, and then DeepSeek, DeepSeek. Okay, now I don't think I referenced port number. Yeah, so I have to update these port numbers as well. So that should be 40, and that will be 41, so they all have unique ports. I don't need to, now in the Ollama pod, let's collapse this. This is where I'm actually going to make the Kubernetes pod with Ollama. So let's go ahead and copy Mistral down to model storage and paste that in one time. And we're going to change this to Phi4. And we're going to pull Phi4. And this is on port 40. And we're going to do this one more time and change this for the DeepSeek information. DeepSeek. Now here I have to go back to here. So we'll pull the DeepSeekV3 model. I wonder how do I... So that's the Ollama. I need to copy this whole name in. Ollama run. I can't just call it DeepSeekV3. All right, so I have to remember that for the Python code. This might take an iteration or two for me to get this working because it's not just DeepSeekV3. So we're going to pull that model. And let me just check the parameter size again. 2 gigs. Okay, so that's not so bad. That's a small model. All right, so now I need to go into the Python code. And we're going to add those models here. Now this is referenced a few times in the menus here. So I want to find this and replace it with Phi4. And just to be safe, let's put the full name in here. We'll try that. All right, so we'll replace all. So now I should present the Phi4 model. The other thing I wanted to change while I'm in here, let me look at my Llama 3. What version of Llama 3 am I using? Now I don't have enough juice to run Llama 3.3, but I would like to run Llama 3.1. So I have Llama pull Llama 3 there. Let's look for Llama 3. So Llama 3.2 is 70 billion. It's way too much for my little system. But there's a Llama 3.1 available in 8 billion. So Llama 3.1. And let's go back to the Python. And change that to Llama 3.1. Whoops, wrong place. All right, let's try that. So now as for the Kubernetes stuff, I have to get my Kubernetes all up and running. So I'll be back with the commands. I have to look this up real quick. And what we're gonna do is build this Kubernetes system, start it and download those models into the individual pods, and then try it out. So I'll be back in a few minutes to finish off this, this activity of getting the Kubernetes up. All right, one other thing, when I was updating these files, we have to update the container port as well as the value for the environment variable. All right, so now I have 2 new models and I'm updated Llama 3 to Llama 3.1. First thing we need to do, right, is make sure Docker's up and running. And we have Docker here. I'm going to do a Minikube delete to make sure I don't have any lingering Minikubes. And then I'm going to apply this command and start a new Minikube using the Docker driver for networking and the container runtime of Docker, exposing all my GPUs, my RTX 2060, all CPUs, and 10 of memory. So once this comes up, we can actually refer to the README file and set up our Kubernetes. So the first thing I'm going to do, it's going to complain and say that this already exists, but I'm going to just make sure that the NVIDIA plugin is created. I'm going to apply a secret so it can read from my environment variable file, so that way it can use OpenAI in the cloud. Apply my Kubernetes load balancer, my Ollama service. Apply the Nginx config, so that way when Nginx, the pod, comes up, it has a configuration. So let's apply the Ollama pod. That's a good sign that there's no errors. And let's go into Kubernetes. Oh, I made a mistake here. Let's delete this pod real quick. I haven't made a mistake. This all worked, but I want to do something in advance. I want to jump into Minikube and download the containers in advance. So I'm going to grab the Nginx container, Docker pull, Nginx latest. I'm going to grab Ollama latest. Now I'm doing this in order to, I have 6 Ollama servers now, or pods. Instead of each of those pods downloading, I can have an image pull policy of only pulling it if it's not present. So I'm making it present in Minikube, the actual Ollama image. That way I don't have to download it 1, 2, 3, 4, 5, 6, 7, or 6 times. And then I'm going to pull my PCAP, my Python code, my Python container. I'm going to pull that in, which reminds me, while that's downloading, I need to do a Docker build. Right, because I updated the Python code. So I need to do a Docker build. Yeah, so just a quick Docker build -t, and then the name of my PCAP, and then I'm going to push it to the cloud. I think I just say Docker push. And it's going to push that new, most of it's already going to exist. It's just the Python update. Okay, so now that that's been done, I can close out of this terminal. And Ollama's pulled. So now let me grab my, and do a Docker pull of that container. Now this will take a few minutes, so I'm going to just pause the video because it does take, 4 or 5 minutes to download the couple gigabit image. We'll be back again. Okay, so if I do a Docker image ls, we can see now inside of the Minikube, we have the PCAP, Ollama, and Nginx images. So now, when I bring up the server, when I apply Ollama pod, a good sign, if I go to my Kubernetes extension in VS Code and go to workloads pods. Okay, that's not great. Usually this should be green. Okay, so I had some system allocation issues. Let's try to bring it up again. I had maybe over allocated too much memory. And I had enough memory and CPU, but once I added 2 new pods. So let's try to apply it and take a look here. This should go green. There we go. Okay. So it was a resource allocation issue. Under each pod here, I just scaled everything back quite a bit. Now I hope that doesn't affect performance of the pods. But now what we want to do is get the logs from one of these pods, all of these pods, and start taking a look and making sure. So let's make sure packet Kate. Okay, so my main front end is up and running here. And then we're going to go through each of the models. So let's go back to our definition file here and collapse everything. And we'll start checking and making sure that the models are downloading. So Gemma 2, pulling manifest is good. Qwen, and I'm not expecting any of these to have problems. Llama 3. Now Llama 3, okay, it should be pulling Llama 3.1. And it looks like that new updated command worked. And now let's check Mistral. And now our 2 new pods. So Phi4. And Phi4 is pulling. And DeepSeek. And DeepSeek is pulling. So, again, I'm going to let these manifests download so that I have the LLM within each of these pods loaded and ready to start answering some questions. Now, I hope the Python code works out. We'll have to see, but we're getting closer to testing these new models. So I'll be back in a little while these pull in the background. Stay tuned. Okay, as you can see, I've got a different shirt, little different hair today. Back in a little while turned into a couple of problems. So let's take an intermission. First problem, the name of the new models that I wanted to try, Llama 3.1 and the DeepSeek with the username / DeepSeek in the path, don't resolve to URLs. So I had to make some aliases in the code, and I'll show you that before we continue. The other thing is Phi4 uses 14 gigabits. That's the parameter size. And I didn't allocate enough Kubernetes resources to that particular Ollama pod to handle the overhead of the much larger, comparatively speaking, model. So I'll show you both of those things in the code, and then we're going to proceed with actual successful working consensus AI by adding these 2 new models and adjusting Llama to be Llama 3.1. Let's keep going. The 2 issues that I just spoke of, if we look at the packet Kate code, my code that does this, I'm using a URL, an API, right? Well, this path doesn't like Llama 3.1, and it definitely doesn't like, this username DeepSeekV3. A bunch of illegal characters here. But later in my code, when I need to reference the model, I still need to actually call the full path name in my code against the LLM. So that was problem 1. Problem 2, in my pods, in my specs, let me minimize all these pods to show you what we've done here again as a reminder. We have our Nginx pod for the reverse proxy, my packet Kate pod for the Python code and the Streamlit app, and then we have these other models. We've added Phi4 and DeepSeek, and we've adjusted Llama 3 to use Llama 3.1. So in the Phi model, I needed to allocate quite a bit more resources, comparatively speaking, to my other model pods. Now this mix does seem to actually let it work. So the next thing I had to do was bring up all my Kubernetes commands, right? So we had the apply Ollama pod command to apply this pod to our Kubernetes. And then we can do the logs. So I shouldn't have closed that. Let's minimize this again. And let's check in on our various containers. Right? So if we look at our Nginx pod, whoops, we can see that it's ready and listening to be our reverse proxy. If we check out the packet Kate container, we can see that Streamlit is up and listening on localhost. If we check our individual models, Gemma 2, not packet Gemma 2, sorry, Ollama Gemma 2, we can see that it's downloaded the 5.4 gigabit model successfully. And if we check Qwen, it's downloaded the 2.3 gigabit parameter model successfully. And if we check Llama 3, it should have the Llama 3.1, which is almost 5 gigabits. Okay, and we're going to keep going. Mistral, and Mistral's a little over 4 gigabits. And then a couple of our new models, Phi4. Now Phi4 is a whopping 9.1 gigabits and 14 billion parameters. And DeepSeek is actually the smallest of the models at around 2 gigabits and 3.4 or 3.2 billion parameters. All right, so we're going to go into our front end. Let me fix the zoom here. We're going to select all of our models. Remember, we're trying to do consensus. So we're going to check all our models and we're going to upload a simple packet capture. And to show you that we're not cheating, let's actually look at that capture in Wireshark so we know the valid answer. So the source is 192.168.2.61 and the destination is 172.170.169.30 using UDP and port 9000 as the destination port. So we can proceed to chat. And I like to factually check these models to see if they can participate in my retrieval augmented generation solution. So we have a RAG pipeline here. And let me show you the RAG pipeline as a visual. And if you just Google LangChain RAG and go to images, you're going to find this image. And, whoops, I don't want that. So our source in this case is a packet capture. Now there isn't a packet capture loader. What I'm doing is transforming the packet capture into JavaScript object notation, loading it as JSON, transforming it into small chunks with a semantic chunker, embedding it with the OpenAI embeddings API, turning it into floating point numbers of vectors, storing them in ChromaDB, the vector store, and then using Ollama in different pods to do the retrieval. So we're going to make API calls to each of those models we just described, asking it the question and trying to get the correct answer. Now that's the first pass. We then make a secondary pass, passing the answers from the question and the original question back to each LLM to say, listen, here's 6 different models' answers. Can you all come to a consensus as the best answer given the retrieval augmented generation vectors and given each other's answers? Now this is going to take some time, and I'm not sure which model we're in right now. So we can check these logs again, and we're going to see. So right now, I'm in the Gemma 2 model. It is in my GPU here. And if I were to load my task manager and take a look at the GPU, we're going to see that it's pretty much pinned out, the GPU memory and the GPU CPU. Because Gemma 2 here is trying to answer that question using the retrieval augmented generation. Now, what's kind of neat is we're going to see kind of a roller coaster effect where the GPU spikes when each model is in the GPU, and then it's going to flatten off and then spike again and then flatten off and then spike again. So we don't have an answer yet. Gemma 2, as we talked about, is a fairly large model for a small language model, 5.4 gigabits. And again, this is an RTX 2060. We should be able to see that here somewhere in the logs. Right here, right? CUDA 0 is the device with that much megabits free. And then it's loading up the Gemma 2 model and generating the token response. So I don't want to stop recording because I'd like you to get a sense as to how long each model takes to answer, as well as the quality of their answer. So again, this is the sort of information that we're looking for. So here we go. Here's Gemma 2's response. And now it's moved on to another LLM. So we can see the memory, the GPU is collapsed, and now it's entering the next GPU. Right? So we're going to watch it flatline, and then it's going to spike up again as it enters the next GPU model. Now, I'm not sure what the next model is. And you can see Gemma 2 is all done here with the GPU. We can see there's the post to the API that we're using. So we're just going to have to like check the other models. Qwen. It's not in Qwen. Llama 3. So it's in Llama 3 now. And Llama 3, again, if we take a quick look, it is 5 gigs? Yeah, about 5 gigs. And we can see that it's using my RTX and how much megabits free. And it's in inference. So there's Llama 3 has responded. So let's take a look. Gemma 2, they both agree. And where's our Wireshark here? Are these correct? 192.168.2.61 as the source, correct. 170.72, 169.30, also correct. And there's Mistral's answer, which is also correct. So 3 out of 3 of these models are able to take a packet capture and identify source and destination IP using the retrieval augmented generation. And you can see how long each of them roughly took, right? This is a great approach. I'm going to try to quickly switch back. This is a great approach for a few different things. One is just to test model performance. I can load up as many different models as I want in Ollama pods, download the models into those pods, and do inference testing in a for loop. Test this model, test this model, test this model, and get a sense as to which models we start to trust, which models are giving us better answers, which models are able to perform retrieval augmented generation as the retrieval engine in the chain that I showed you. So another great way is when new models come out to compare them against older models or previous versions. I could have a Llama 3, a Llama 3.1, a Llama 3.2 discrete pod and do this and see how different Llama models start to answer. So let's switch back. And we have Qwen's response. Okay, here's the first incorrect response. The source is some MAC address, but it has the destination IP correct. Now, this isn't the first time I've seen Qwen get things wrong. Let's take a look at the Qwen logs to take a look at the model. It's a very small model. So it's only 2.3 gigabits in size, disk space size, and I'm not sure how many parameters it has. We can quickly look that up on CUDA. But it consistently gets 1 out of 2 wrong, either the source or the destination. Right? So I don't trust this model as much as I trust the other models. It's also why I'm doing this consensus approach, is because ideally when this council of artificial intelligence evaluate each other's answer in the second pass and the third pass, this incorrect answer is going to be highlighted as an anomaly and thrown out and filtered out and boiled out as being incorrect. That's the whole purpose of this council of oracles, this democratic consensus approach, where Gemma is going to look at all the other answers and Llama 3 is going to look at all the other answers, and they're going to be able to tell me, the human, listen, this one model got it wrong. You should trust us as a council and ignore that MAC address as a source IP. Now, as a network engineer, I know this is incorrect. Most lay people should be able to understand that this is a MAC address, not an IP address, and therefore it's incorrect. But I don't want to make any assumptions. So I believe I'm in the Phi4 model right now, which is taking a long time to do its inference. And I have given it just enough space and just enough computer resources to actually function, even though it's almost 10 gigabits in size on my RTX box. But as you can see, it's just churning through the resources here. Everything is pinned, and we don't have an answer yet. This may take minutes. It won't take tens of minutes, maybe. It won't take 30 minutes or an hour. However, we are going to have to be patient while it comes up with its answer. The other thing I'll do is, once we have the original batches of answers from these models, I'll pause the video and then come back and we'll revisit what the consensus approach, the consensus algorithm came up with. So it's just chugging away here. Right, there's the model size, 8.43 gigabits. I don't know if there's a human readable parameters value here that tells us how many parameters the model is. Yeah, we still don't have an answer yet, but it's not crashing or anything. It is just literally churning out the tokens to give us Phi4's answer. Now, on Phi4, one common criticism of Phi3, Microsoft Phi3 verbosity, right? It feels obligated to explain its reasoning. Is there any way to adjust the verbosity? You're going to see a lot of people talking about how verbose Phi3 is and just how chatty it is. So part of the reason why it's taking so long to generate the answer is that I doubt Phi4 is going to come back with just a one-liner that gives us a source and destination. Phi4 is probably going to do like a full-blown packet analysis and be very verbose and very chatty, which is fine. But as you can see, it does take longer to generate the response because of the number of tokens Phi4 feels is necessary to answer a pretty straightforward question. I think we've been waiting for Phi4 as long as we waited for the first four models to answer. So let's just pause it here and I'll come back when we have Phi4's answer. Now, unfortunately, we might miss how quickly or how long it takes DeepSeek to answer, but I'll be paying attention here and hopefully be able to share this. Oh, there we go. Okay, good. Okay, so Phi4 is done. It's dropping out of memory here. And the last model is going to be the new DeepSeek model. And it looks like it's probably already done. No, it's going to be close though. So DeepSeek again is very small. It's very small. Less than 4 billion parameters, 2 gigs in disk. And here is Phi4's response in the meantime. Source, and it even breaks down. See what I mean about the verbosity? Based on the provided packet capture data in JSON format, we can extract information regarding IP addresses involved with this communication over Wi-Fi. So it knows it's Wi-Fi. I didn't ask that. Here's the source IP based on the actual field, right? So it justifies its answer or backs up its answer with its source of truth. IP is correct. IP destination field is correct. To summarize, here's the source and destination. And then, some text about the rest of the answer. Now, DeepSeek is already done. And check out DeepSeek. It's correct. Okay? So let's come back to the screen real quick. So a couple of things here. DeepSeek at 2 gigs. 2 gigs. You could put it on a thumb drive. You could put it on a micro SD card, right? An LLM that can do RAG and answer questions like source, destination, IP. It outperformed Qwen, which got something wrong. Quite remarkable. Very, very powerful, small, fast, reliable model. Phi4, verbose still. Awesome extra information. Awesome context. Awesome text response. Llama 3.1, correct answer, very fast, very succinct. So, what's happening now in the background, just to remind you, is that I'm taking all of these answers now. All of these answers are in my next prompt. And if I could find the prompt very quickly, I'm, saying, hello, esteemed models. I'm seeking your collective expertise to reach a consensus on the following question, the original question. Below are the individual responses from each model. All results. Everything you see here. Whoops. Where did that go? Please review these responses carefully and provide a reasoned summary that attempts to align and synthesize the varied perspectives. Consider the strengths and weaknesses of each response and aim to come to a common themes or point of agreement. And then I have a final prompt that's very similar, that's taking the consensus answers and running it finally through another filter to come to a so-called final best most agreed upon answer. So we're going to have to wait a while. It's probably in Gemma 2 right now. So if we check in on the Gemma logs. What? Oh, Gemma 2. So, right, here's the first answer and a few logs. And now I've re-entered the GPU for its consensus algorithm. All right. So what I'll do is I'll let all the consensus finish in the background, and then we will wrap up this video and see how well all they do, and see if we can come to the conclusion using consensus and these new models and new versions of models to see if they all agree that these are the correct source and destination IP addresses. All right, we'll see you soon. Okay, so I think it's finished, and it's a little verbose, and I know that it might be overkill, but the whole point here is to bounce the answers off of each other. So here's the original batch of answers. Of these answers, one of them is incorrect with the MAC address. All right. So unfortunately, the Gemma model timed out on the first consensus. That's unfortunate. But Llama 3's consensus, right? After reviewing the individual responses from each model, I will attempt to summarize their collective perspectives and identify common themes. And it explains here that this model's response is slightly off as it incorrectly identifies the source IP as a MAC address rather than an IP address. Right? And, from the common themes of points of agreement, the conclusion is that these are the source and destination IPs. Mistral comes to similar conclusions, and then Qwen actually corrects itself with the information from the other models, the correct source and correct destination. So that's interesting. It is actually able to reconcile the fact that it was incorrect based on the other answers from the other models. Now, Phi4 has the common agreement, 4 to 5 models consistently identify the source and the destination. The Qwen presents an anomaly, which appears to be a MAC address, either a misunderstanding or misinterpretation of the data. Strengths and weaknesses, synthesis, summary. Despite the outlying response from Qwen, the overwhelming consensus across multiple models supports the conclusion that the source is this and the destination is this. Right? And again, another consensus model from DeepSeek. Just a remarkable model, given how small it is. This is incredible stuff. That it actually comes to the conclusion, right? And then the final consensus, just a final pass. And we can see everybody's getting it right by this point in the final pass. Everybody comes to the correct conclusion based on the consensus, right? Unified source and destination, final answer. So we've specifically incorporated the new models, Llama 3.1, Phi4, and DeepSeekV3 into the consensus Kubernetes jukebox, like I call it. Different Ollama pods, different port numbers, different URLs in the reverse proxy to make the API call and pass the retrieval augmented generation system from the LangChain. Again, I'm super impressed with DeepSeek, given its size. I'm very impressed with Phi4. Phi3 was never able to do this packet analysis. You can look at some of my older videos and older attempts at this. Phi3 was just never good at this rag. I have personally just witnessed the improvement from Phi3 to Phi4 for my own purposes with retrieval augmented generation and packet analysis. Llama 3.1, awesome. Just really good stuff for a 5 gig model. So check out the repo, check out the code, try this yourself. I'd love to hear what models you're using. If you have any suggested models that you'd like to see me try, just reach out to me. Thanks again.